In the quiet autumn of 1979, deep inside a guarded workshop near Stuttgart, German machine builders stood around a heavy metal cabinet. Outside, cold rain slicked the cobblestones of Weilimdorf. Inside, high-voltage static and fresh ozone filled the dark room. An engineer engaged a high-pressure gas system. No heavy flywheel turned. No air clamps hissed. No heavy iron ram crashed down onto metal. Instead, an invisible beam of carbon dioxide laser light shot down a clean glass tube, bounced off polished copper mirrors, and struck a plate of structural steel. Cold metal melted into liquid vapor in seconds, without mechanical shear touching the plate. Behind this miraculous light beam lay a dangerous financial emergency. The laser generator firing inside that cabinet was imported from an American supplier under strict contracts. The foreign seller controlled spare parts, capped power output, and scoffed at European builders mastering quantum optics. Worse, the machine carried a fatal design flaw. Its imported optical mirrors degraded after 40 hours of continuous shop cutting. If word leaked that this new laser press was a financial time bomb, the firm faced immediate bankruptcy. The entire enterprise rested on Berthold Leibinger, an engineer who started as an unpaid worker. Welcome back to Rivet and Rebar, where we dig into the industrial giants and mechanical sagas that built the modern world. If forgotten industrial history and precision engineering are your thing, take a moment to hit that subscribe button right now and turn on notifications. Now, back to where it all began. The story of TRUMPF does not start in clean labs, but in post-World War I Stuttgart. In 1923, machinist Christian TRUMPF purchased a modest workshop owned by Julius Lusser. The shop manufactured flexible shafts, beijwellen, twisted wire coils in rubber sleeves. These transmitted motion from electric motors to grinding wheels, dental drills, and metal shears. It was grueling, low-margin benchwork, where success was measured in pfennigs and survival required low overhead. Across the Swabian Valley of southwestern Germany, manufacturing was a sacred duty. Lacking coal mines and deep ports, local engineers survived through precision craftsmanship and hand-scraped tolerances. Into this landscape walked Berthold Leibinger. Born in Stuttgart in 1930, Leibinger entered the TRUMPF shop floor in 1950 as a 20-year-old apprentice mechanic. He swept metal turnings off oil-soaked floors, scraped machine ways by hand with steel chisels, and learned the feel of Mechatronic cast iron beds. Seasoned cast iron swallows vibration better than modern welded steel frames. Young Leibinger absorbed that mechanical truth deep into his bones. He observed how microscopic imperfections in a lathe bed could chatter through a spindle and ruin a precision thread. He also saw how hand-scraped oil pockets preserved smooth movement across decades of brutal factory work. Recognizing his sharp mind, the firm sent Leibinger to study mechanical engineering at the Technical University in Stuttgart. Yet his real education occurred in 1958, when he traveled to Cincinnati, Ohio, then the machine tool capital of the world. Working as a design engineer for the Cincinnati Milling Machine Company, Leibinger witnessed American industrial power at its absolute peak. He studied heavy hydraulic tracing systems, high-speed gear grinding, and automated transfer lines. However, he also noticed a fatal structural vulnerability. American builders favored massive scale and standardized mass production over customized flexibility, shop floor durability, and enduring engineering craftsmanship. When Christian TRUMPF summoned Leibinger back to Stuttgart in 1961 to head development, the young engineer brought back a clear vision. He would marry American production efficiency with Swabian engineering precision. During the early 1960s, sheet metal fabrication across the globe had struck a brutal mechanical bottleneck. Machining solid castings on lathes had progressed rapidly, but sheet metal remained an agonizingly manual endeavor. If a factory needed to cut a complex irregular contour or non-standard cutouts in steel plate, workers were forced to build expensive custom steel stamping dies. Machining, grinding, and heat treating these hard steel dies took weeks of expensive skilled labor. For short production runs or prototype parts, hard tooling was economically impossible. Job shops relied on manual layout benchwork. A machinist scrawled layout lines onto blue scribing die with a carbide tip, clamped the sheet to a heavy iron bench, and hand-cut shapes using mechanical hand shears or reciprocating bench nibblers. The work was slow, dangerous, and exhausting. Manual nibbling left heavy jagged burrs along every cut edge, requiring hours of back-breaking file work and pedestal grinding just to make parts fit together. Cylinder walls flexed, punch pins sheared under off-center loads, and tolerances drifted wild. Imagine running a sheet metal job shop in 1968, where a single misaligned punch stroke meant scrapping an entire day of hand-indexed sheet steel. Berthold Leibinger set out to obliterate this bottleneck forever. His first major breakthrough came with the development of the copy nibbling machine, the CS75, which used a tracing stylus following a master template to guide a high-speed nibbling punch through sheet metal. But Leibinger knew templates were merely a temporary stepping stone. Hanover hosted the true revolution in 1968, where Mechatronic engineers unveiled the Trumatic 20 at the European Machine Tool Exhibition. It was the world's first numerical-controlled sheet metal machining center. Guided by punched paper tape running through an optical reader, the Trumatic 20 replaced manual sheet positioning with an automated two-axis coordinate table, running on recirculating ball screws and hardened box ways. Sheet steel was gripped by pneumatic clamps and moved rapidly under a stationary high-rigidity punching head at speeds never before seen in metal fabrication. Instead of changing tools by hand or relying on turret presses that flexed under load, Leibinger designed a single-station punch head fed by an automatic tool changer. It swapped punches, collet indexers, and dies in under 5 seconds. The machine executed punching, nibbling, and profiling in a single setup. The precision was staggering. The machine held tolerances thinner than a human hair, 1/30th the thickness of a sheet of printer paper. Consider what this meant for a factory floor in 1968. A job shop owner could feed paper tape into the console, clamp a raw sheet of steel plate, and step back while the machine punched hundreds of intricate holes and contours with total mathematical repeatability. Production times dropped by 90%, custom die costs vanished overnight, and transparent upfront pricing transformed job shop economics. The machine was an instant sensation across Europe and North America, but Leibinger was not satisfied. He understood that mechanical nibbling, no matter how fast, still exerted physical shear forces against sheet metal, causing thin gauge plates to distort and thick plates to leave microcracks along the cut edge. To achieve ultimate freedom in sheet metal fabrication, he needed a tool that could cut through heavy steel without physically touching the metal at all. Forged in historical fire, the journey toward that goal required surviving intense international competition. TRUMPF had already survived devastating trials in its past. During World War II, Allied bombing raids targeted Stuttgart's industrial sector. High-explosive bombs smashed factory roofs, shattered machine lines, and buried precision shop tools under rubble. Yet as soon as sirens cleared, TRUMPF's machinists dug their lathes out of the dust, rebuilt shattered shop walls with salvaged brick, and restored production amidst scrap shortages. By the late 1970s, a new crisis threatened European machine builders, the Japanese CNC Blitzkrieg. Companies like Amada, Fanuc, and Yamazaki Mazak flooded Western markets with low-cost punch presses and machining centers. Backed by cheap capital, aggressive vertical integration, and modular designs, Japanese builders undercut European prices by 30 to 40%. Global stagflation and soaring energy costs squeezed job shop margins. Many historic machine tool builders panicked. They slashed engineering budgets, cheapened structural castings, outsourced manufacturing, or surrendered to holding companies. Berthold Leibinger refused to retreat. He recognized that competing on low cost alone was a race to the bottom that would destroy Swabian craftsmanship. Trump's response was to leapfrog competition through radical technological superiority. In 1979, Leibinger introduced the Trumatic 180 laser press, a machine combining mechanical punching with a high-power carbon dioxide laser. It could punch round holes with mechanical dies and cut complex contours with a thermal light beam. But this bold leap plunged TRUMPF directly into the crucible of optical physics. TRUMPF did not build its own lasers. It purchased gas laser resonators from optical manufacturers in the United States. The decision nearly destroyed the company. Imported laser resonators were delicate laboratory instruments never designed to withstand the violent acceleration, metallic dust, oil mist, and three-shift vibration of a job shop. Laser gas mixtures contaminated rapidly, optical mirrors misaligned under thermal load, and direct current electrodes corroded inside laser tubes. Worse, American export regulations created severe supply chain bottlenecks, leaving European customers waiting months for replacement optics. Japanese competitors seized on these failures, broadcasting that laser cutting was an over-engineered gimmick. Foreign banks tightened credit lines, and board members urged Leibinger to abandon laser technology. They held the line. Here is where the opening mystery unspools. In 1985, at the age of 55, Berthold Leibinger took the biggest gamble in industrial history. Facing choked foreign supply chains and mounting field failures from imported optics, he made a secret executive decision. TRUMPF would stop buying American lasers entirely and design its own industrial carbon dioxide laser from scratch inside its factory at Ditzingen. Industrial experts and academic laser physicists laughed at the proposal. They insisted that a Swabian machine tool builder had no business trying to master quantum electronics and optical resonators. Building a laser required clean rooms, ultra-pure gas handling, and high-frequency electrical engineering, disciplines foreign to heavy iron machinery. Leibinger ignored the doubters. He transformed a wing of the Ditzingen plant into an optical laboratory, hired brilliant young laser physicists, and gave them authority to rewrite laser engineering. The breakthrough came when Leibinger's team identified the root cause of imported laser failures. Traditional industrial lasers use direct current electrodes placed inside the gas discharge tube. Sparks pitted metal electrodes, sputtering copper particles onto internal mirrors and corrupting gas mixtures. Leibinger's team discarded direct current excitation entirely. Instead, they invented radio frequency excitation. They placed high-frequency electrical electrodes outside quartz discharge tubes, coupling radio waves through tube walls to ionize gas without physical contact between metal and gas, to circulate gas at supersonic speeds without oil contamination. They integrated magnetic bearing roots pumps. The result was the legendary TLF-1000 carbon dioxide laser. The TLF resonator produced a laser beam of unbelievable spatial mode quality and thermal stability, housing a folded resonator tube inside a rigid frame that swallowed shop floor vibration. When American suppliers realized Trump was canceling contracts, they attempted to block market entry by threatening patent litigation. But Leibinger had secured proprietary international patents for his RF-excited laser technology and established in-house mirror polishing facilities. When the secret TLF laser was officially unveiled, it did not just match foreign imports, it shattered them. Continuous laser cutting operating hours leaped from dozens of hours to thousands of hours without optical maintenance. Operating costs plummeted, beam power doubled, and TRUMPF established total vertical integration, controlling every component from steel frame to quantum light source. The gamble succeeded completely. While TRUMPF built its laser empire on engineering mastery and long-term capital reinvestment, a tragic contrast was unfolding across the Atlantic. During the late 1970s and 1980s, the historic American machine tool industry, once the undisputed titan of global manufacturing, was systematically dismantled by Wall Street conglomerates, private equity asset strippers, and corporate raiders. Legendary American builders like Cincinnati Milacron, Pratt & Whitney, Warner and Swabian, and Kearney and Trecker were absorbed by financial holding companies that cared nothing for cast iron ways, spindle tolerances, or apprenticeship training. Financial engineers replaced mechanical engineers in executive suites. To meet quarterly profit targets and boost short-term stock prices, corporate managers cut research budgets, sold off foundry assets, outsourced component fabrication, and stripped cash reserves to fund stock buybacks and executive bonuses. When foreign competition intensified, these financialized conglomerates lacked technological capability to innovate. Instead of building better machines, they filed trade protection lawsuits, begged for government bailouts, and eventually liquidated iconic manufacturing plants across Ohio, Connecticut, and Wisconsin. Thousands of master machinists were laid off, technical archives were tossed into dumpsters, and historic machine shops were auctioned off for scrap value. Berthold Leibinger watched this destruction with profound sadness and fierce resolve. He vowed Trump would never suffer the same fate. He stubbornly resisted all pressures to take Trump public on the stock market. Knowing public listing would subject the firm to quarterly earnings calls and impatient institutional investors, Leibinger reinvested up to 10% of TRUMPF's annual revenue directly back into research and development every single year, even during severe economic recessions. He established a binding corporate constitution locking voting rights within the family foundation, ensuring management could plan for decades rather than quarters. When financial analysts advised him to cut costs by buying cheap components overseas, Leibinger doubled down on vertical integration, building internal capabilities for optic polishing and induction hardening. Quality was non-negotiable. He held the line. Today, corporate raiders who gutted the American machine tool industry have faded into historical obscurity, their paper empires long liquidated. But the heavy iron built under Berthold Leibinger's watch refuses to die. Walk into custom sheet metal job shops from Chicago to Stuttgart, from Tokyo to Monterey, and you will find 40-year-old TRUMPF punch presses and early laser cutting centers still hard at work. Their paint may be chipped and guards scratched by decades of shop floor use, but beneath the surface, their seasoned Mechatronic cast iron beds remain as dimensionally stable as the day they were hand-scraped by Swabian apprentices. Modern job shops routinely retrofit these vintage machines with solid-state fiber lasers and digital CNC controllers. Mounted onto 4-decades-old structural iron frames, these hybrid systems cut stainless steel and titanium with 10,000th of an inch precision. Berthold Leibinger passed away in 2018, having transformed a modest Stuttgart workshop into a $5 billion global laser giant. Yet his true legacy endures in physical permanence of heavy iron machinery operating across the globe. Corporations go bankrupt, founders die, and financial bubbles burst, but seasoned cast iron machinery built with unyielding integrity outlives the empires that created it. The company evolved. The iron outlived them all. You are watching Rivet and Rebar. If you enjoyed this deep dive into the mechanical mastery of TRUMPF and Berthold Leibinger, hit the like button and subscribe for more forgotten industrial history. Click the video on your screen right now to explore our next documentary on heavy iron engineering.